So we have seen this in the previous class. The d orbitals, which are degenerate, undergo splitting into two. They are T2g orbitals and Eg orbitals, and the energy gap between T2g orbitals and Eg orbitals are delta O, or it is called 10dq value, or that is the crystal field splitting energy, and each T2g orbitals are stabilized by an energy of 4dq, while each Eg orbitals are destabilized by an energy of 6dq, and this energy separation is delta O, or 10dq value. So we have seen and we have explained which are the T2g levels. dxy, dyz and dxz are the T2g levels, while dz square and dx square minus y square are the Eg levels. This is the crystal field splitting happen in an octahedral field. So we have seen this in the previous class. Now we have to discuss what are the factors that affect the magnitude of 10dq or delta value. We know 10dq is the energy gap between the T2g and Eg level in an octahedral field. So what are the important factors that affect the 10dq value, whether it is an octahedral complex or a tetrahedral complex or a square planar complex? So we are generally speaking, what are the important factors that affect the crystal field splitting value 10dq or delta? The first factor is the oxidation state of the central metal ion. When the oxidation state increases from +2 to +3 oxidation state, the magnitude of 10dq value will increase approximately to 50%. That means for any metal ion having same ligands, but the metal ions are in different oxidation states. If in a same geometry, as the oxidation state of the central metal ion increases, the 10dq value increases. That means when we move from +2 to +3 oxidation state, +2 to +3 oxidation state, the value increases by 50%. This is because as the oxidation state increases, the positive charge increases. This helps the ligand to come closer towards the metal ion, and hence the field strength increases. So the crystal field splitting increases. So we could say when the oxidation state increases from +2 to +3, the crystal field splitting value increases by 50%. See the example? I have cobalt NH362 plus ion. Here cobalt is in the 2 plus oxidation state. And I am taking another complex where cobalt is in the +3 oxidation state. The metals are cobalt, the ligands are ammonia, but the oxidation state of one is +2 while another is +3. That means the oxidation state changes from +2 to +3. See, for the first complex, the 10dq value is 10,200 centimeter inverse. That is the energy gap between T2g level and Eg level. See, for the second complex, the oxidation state is +3. The value is 22,870. That means when the oxidation state increases from +2 to +3, the 10dq value increases to 50%. See another example. I have FeCN6 4-. FeCN6 4 minus. In this particular complex, the ion is in the plus 2 oxidation state, while here ion is in the plus 3 oxidation state. FeCN6 3 minus. So this is a plus 2, this is a plus 3 ion. See the value? For the first compound it is 32,200, while for the second compound is it 35,000. So we could say, as the oxidation state of the central metal ion increases, the 10dq value increases. Take down. The second factor that affects the value of 10dq is the geometry of the coordination compound. That means we have to consider whether the compound is a octahedral, tetrahedral, or square planar. So depending upon the geometry, the 10dq value will undergo change in magnitude. So I am taking same compound, but they are in different geometrical arrangement. For example, I am considering tetrahedral and octahedral complex. It is observed that the crystal field splitting of octahedral compounds are greater or larger than the crystal field splitting of tetrahedral compounds. So, as per the geometry concerned, octahedral complexes are having greater 10dq value or greater 10dq splitting than tetrahedral values. See here. So tetrahedral complexes have smaller 10dq value than octahedral ones. So we have to find out how the quantity connected or related for octahedral and tetrahedral complex. See here, 4.4 dq of octahedral is equivalent to 10 dq of tetrahedral. That means tetrahedral 10 dq is smaller compared to the 10 dq of octahedral. So we can say the splitting of d orbital is maximum to octahedral complex than tetrahedral complex. See here, I am taking two compounds. One is CONH3 6 times, 2 plus oxidation state. Another same compound, but it is a tetrahedral compound, CONH3 4 times 2 plus. So the metal is same, the ligand is same, oxidation state is same. But one is an octahedral complex and another is a tetrahedral complex. For octahedral complex, the 10dq value is 10,200, while for tetrahedral it is only 5,900. So we could say, comparing tetrahedral and octahedral complex, the 10dq value of octahedral complex is greater than tetrahedral complex. Now we have to see about square planar complex. See here, square planar complex have greater value than octahedral complex. So when we consider square planar, octahedral and tetrahedral complex, the 10dq value is maximum for square planar complex, and the relations they are related as, see here, 1.3 delta value of square planar is equal to 1 octahedral value, that is equal to 4.4 tetrahedral value. That means the 10dq value of square planar complex is greater than octahedral complex, which is greater than tetrahedral complex. Take down. The third factor which affect the magnitude of 10dq value is the nature of the transition series. We know we have 3D transition series, 4D transition series and 5D transition series. So I am considering in a same group elements from 3D to 4D to 5D transitions. So when we move from the 3D series to 4D series to 5D series in the same group, that means from top to bottom, the 10dq value increases. That means the 10dq value for 5D series is greater than 4D series and 4D series is greater than 3D series. So we could say the third factor is the increase in transition series from 3D to 4D to 5D. So heavier atoms are having greater delta Q delta value, delta or 10dq value. See here, I am taking the same complex, but the metals are different. Metals are cobalt, rhodium and iridium. Cobalt belongs to 3D series. Just down we have rhodium 4D series and just down we have iridium 5D series. So we move from 4D to 3D to 4D to 5D. See the values of 10dq. The 10dq value increases from 22,000, then to 34,000, then to 41,000. So we could say when we move from top to bottom in same group, that is from 3D to 4D to 5D series, the 10dq value increases. Take down. The fourth factor that depends upon the magnitude of 10dq is nature of the ligands. Depending upon the ligand, the 10dq value increases. Some ligands interact with the metal or the d orbital very weakly, while some ligands interact with the d orbital very strongly. So we could say the interaction of the ligand with the metal ion affects the 10dq value. So strong ligands split the d orbital to maximum while weak ligands split the d orbitals to minimum. So depending upon the splitting up of this 10dq value or d orbital, or depending upon the strength of the field, ligands are classified or arranged in a series, and that series is called spectrochemical series. So spectrochemical series will give you the idea which ligand is strong, that means maximum splitting to d orbital, or which ligand is weak, that is minimum splitting to d orbital. So we could define spectrochemical series is a series of ligands, or the ligands are arranged in a series by the increasing order of their field strength or ability to split the d orbital. I am giving you a brief description of that one. See, I minus is a weak ligand while Cn minus is a strong ligand. So this order is called spectrochemical series, and I am giving only very few ligands here. So I minus and Br minus are weak ligands. The crystal field splitting is minimum, while Cn minus and NO2 minus and Cn is also there, CO is also there, carbon monoxide is there, are strong ligands. They split the d orbitals to maximum. See here, these are the weak ligands and this end is the strong ligand. So CO, carbon monoxide, is the strongest ligand as per spectrochemical series, while I minus is the weakest ligand as per the spectrochemical series. Very, very important. Take down. See, I minus and Br minus up to water are weak ligands. One of the classification. While from NCS to CO they are strong ligands. And see here, weak ligands have only weak interaction. Hence delta is very small. Delta is very small means it gives rise to high spin complexes. High spin complexes. That we will see later. Still you just take it. While strong field ligands, the interaction is very strong. The splitting is maximum. So it gives rise to low spin complexes. So whether a complex is a high spin or low spin is determined by the ligands. So ligands are determining whether a coordination compound should be high spin complex or low spin complex. Take down. So we have seen the crystal field splitting in an octahedral field. This is the energy diagram or the crystal field splitting diagram for an octahedral field. And now we are going to enter electrons into these orbitals. When electrons are entered into T2G or EG orbitals, it should follow Aufbau principle. What is Aufbau principle? Electrons are entered into the orbitals in the increasing order of their energy. That means the first electron will go to the lowest energy orbitals. Then during filling of electron, we have to consider about Hund's rule. What is Hund's rule? Pairing of electron can only occur all the available orbitals are half filled. And we have to think about the Pauli's exclusion principle. What is Pauli's exclusion principle? An orbital can commit a maximum of 2 electrons. So, after crystal field splitting, we have to enter electrons to T2G and EG orbitals, obeying Aufbau principle, Hund's rule, and Pauli's exclusion principle. The diagram is clear for you. I have 5 unsplitted or degenerate d orbital, and in an octahedral it is going to split into 2. They are T2G levels and EG level. Each T2G orbital is having an energy of 4 dq, while each EG orbital is having an energy of 6 dq. The energy gap between T2G and EG levels are 10 dq or delta O if it is an octahedral field. Is it okay for you? Now we proceed for filling up of the electrons. Now see here, this is the EG levels and T2G levels. EG levels and T2G levels. So I am going to think about a weak field and a strong field. If it is a weak field, the energy gap is very small. If it is a strong field, the energy gap is very high. So 10 dq value will be high for strong field ligands, while 10 dq value is minimum for weak field ligands. And weak field ligands will give rise to high spin complexes, while strong field ligands will give you low spin complexes. So I am going to enter electrons to these orbitals in a high spin or a weak field environment and a strong field environment. Now we see for a D1 system how the electrons are entering and how we could calculate the crystal field stabilization energy for a D1 system. See here, for a D1 system we have a weak field environment. That means I am considering a D1 system in a weak field or the ligand is very weak. In such case, the first electron will enter to the T2G orbital, which is having minimum energy. Okay, so the first electron will be entering to the T2G level, which is stabilized by an energy of 4dq. Now see here, if I consider a strong field, what will happen? The energy gap will increase. This is the T2G level and this is the EG level. So the energy gap is increasing, and here also the electron will enter into the T2G orbital because T2G orbital is having minimum energy. Hence, I could say the configuration of a D1 system is T2G1, T2G1, and the crystal field stabilization energy is 1 into, see, the energy of the T2G level is 0.4 dq or 4 dq. So we could say 1 into 0.4 dq, that is equal to 0.4 delta O, or better we could say it is 1 into 4 dq, that is 4 dq. That is, a D1 system is stabilized by an energy of 4 dq. So when a particular D1 system in a weak field or a strong field, their configuration becomes T2G1 and the system is stabilized by a crystal field stabilization energy of 4 dq. So if we have to calculate the crystal field stabilization energy of a D1 system, whether it is in a weak field or a strong field, we could write the electrons are entering into the T2G level. Hence, the configuration is T2G1 and the crystal field splitting is 0.4 delta O or 10 dq. Okay, you got the point? Take down, very important.